Okay, so we have spoken about self-organization, how different components can interact to give rise to collective properties and behaviors. And we also saw example of voids that we will discuss today a bit more. And today we will discuss about dynamics, which is basically the study of change. And as we can see, change is prevalent, it's constant, it's everywhere. And it's great that we have tools to study it systematically. We would like to have better tools because they are limited in many different ways, but it's something that we have to face. And we could say that its opposite would be stasis or lack of change, which is easier or to describe. Many descriptions of the world, many models are static or tend to a steady state. So we can start with Parmenides in ancient Greece, that let's say his view is that things are and then they don't change, as opposed to Heraclit, who we could say is champion of dynamics because everything is in flow, and also students of Heraclit and his followers. In Buddhist philosophy, we can have both, but let's say according to their ontology, only things that don't change are real. And then if something changes, then it's not real, because if it wasn't before and now it is, then probably it will not be in the future, then it's not really real. But those are different descriptions. Many so-called steady states or attractors, they can be seen as solutions for many problems. So for example, in economy, well, in classical economics, they use mathematical models and they speak about uh, markets clearing, basically when they reach some sort of equilibrium. But that has never been observed experimentally because, let's say, people continue buying and selling, and also we can say that it's only in toy models or very specific games where we have a finish point, and then let's say we can start and then there's some change and then we finish with some configuration. In reality, let's say perhaps this idea of infinite games might be more appropriate because we keep on playing constantly. Of course, there are stages and then there are transitions and then there are places we want to reach, places we want to avoid, some change that we prefer, some change that we don't like. So anyway, rather than to say that we should focus only on stasis or only on change, we should combine both. And to study change, people develop calculus, differential equations. These are limited when we have scale-free like distributions because you don't have a well-defined mean. And let's say we have uh, dynamical systems theory for discrete and for continuous systems. And also more recently, chaos has been related to change. We can say that the more change there is in a system, the more chaotic it becomes. And I mean, there are many different things that we can say that lead to chaos. Also, the more interactions or connections between the components of a system, then the probability of change propagating through that system is increased, and then that leads to chaos when we cross a certain threshold. Also, when we have complexity, meaning interactions, the more interactions we have, the more multiplicative the system becomes, meaning that one change affects others. So then the change propagates in a multiplicative way rather than in an additive way. And this is when we have very few interactions or no interactions. then we make one change and that doesn't propagate. So we can just add the changes of components and that will be the change of the system. When there's strong connections, one change in one element multiplies or propagates through the system. It can be just a bit or it can be a lot, but it's usually multiplicative process. And that's basically nonlinearity. Linear systems means that we can represent it with linear equations, basically without exponents or with exponents 1. Because in geometry, lines are represented like that, like y equals mx plus c or something like that. And then when we have multiplicative processes, then we have polynomials of different degrees, like y equals ax squared. So if we have exponents different from 1, that's nonlinear, and that's a result of having multiplicative processes. And of course, that change has its peculiarities. It's more difficult to predict than linear change, or so. Originally, thermodynamics studied also, like many other branches of physics and other disciplines, try to focus on equilibrium to which thermodynamic systems tend to. And let's say a gas, it's a highly chaotic system if we focus on individual components because they're all kind of colliding, and then it's very difficult to predict. But then since they more or less change at the same scale, we can average them, and then we can use statistics to describe the behavior of the system. So for example, temperature, we can say that it's property depending on the average kinetic energy of the molecules of a gas. And then it will be difficult to measure temperature of a single molecule. But of course, let's say we can easily measure and define it as an average. However, people also started studying non-equilibrium thermodynamics because many phenomena that are interesting for us, including living systems, are far from thermodynamic equilibrium. Thermodynamic equilibrium is also a state of maximum entropy or maximum disorder, meaning that we cannot distinguish one part of the system from another. You might know this idea of we have like a box of gas with a division, and then one part has higher temperature than other, and then we remove the division, and then they initially they have lower entropy because, let's say, there's a distinction between molecules in one part of the box and those in another part of the box. And actually we can make work because, let's say, there's some transfer of energy from one part to the other, and we can use it as work. And this idea of Maxwell's demon, it's, let's say, it's higher intelligence that if it has a gate, that if we have a system already in equilibrium with maximum entropy, but then let's say the average kinetic energy of the molecules, it's let's say certain temperature, but some will have higher than others. So then this idea, if the demon can let go fast molecules into one side and then close the door and then open it again and let slow molecules to the other side, then we could have a transition from high entropy to low entropy, and then we could extract work from that. And that will go against the laws of conservation of energy, that will go against the second law of thermodynamics. But if we consider that the demon would need energy to open and close the gate, then nothing is violated. It's just that you are using that energy to create more potential energy. which is similar to what people use in hydroelectric plants. So if they have excess energy, they use that excess energy to pump water back up the waterfall or the difference of altitude, so that they have more potential energy in the dam. And then when they need the energy, they just use more water. Um, so I mean, in the paper that you discussed, we also uh, I mean they discuss this idea of systems far from equilibrium, and Prigozhin got a Nobel Prize for his contributions to thermodynamics, but initially people consider him a charlatan. I mean, we have heard this, that it seems it's a common topic for people who come with new ideas. Then the established scientists tell, "Oh, you're crazy," um, because they would tell him that his reactions would violate the second law of thermodynamics. And you might have heard of the Belousov-Zhabotinsky reaction, which it's very popular in pattern formation. So you put uh, some chemicals, and then they start creating spirals of different colors. So they're like the two bands. And when Belousov first published this in the Soviet Union, it was rejected because they told him that it could not be possible, those results, because of the second law of thermodynamics. Uh, of course, it's possible because, let's say, it uses some external source of energy and also some properties of the chemical ingredients. And after some time, let's say the fuel for the reaction runs out, and then let's say this part stops. And Jabotinsky later rescued those experiments that were buried for a few decades, and uh, I think it was Winfrey who kind of brought them to outside Soviet Union, and then Jabotinsky ended up in Boston, but I forget whether in Boston University or in Brandeis. I think in Brandeis. Yeah, in Brandeis. Uh, yeah, Irv Epstein was collaborating with him. Different Epstein. uh, but anyway, one of the challenges that we have describing dynamics is that in many systems we will have states that will never be repeated. So every state is new, and most potential states are never visited. So, for example, we already mentioned that most of all chemical reactions will never occur in the universe. Most combinations of genes will never happen. However, the universe is not random. And models can be continuous or discrete, and different aspects of the model can be continuous or discrete. So we have already mentioned this. So we can have time continuous or discrete, space or information continuous or discrete, or values of variables continuous or discrete. So for example, differential equations usually have continuous time, space, and values. Cellular automata and other discrete dynamical systems have discrete time, space, and values. And each one has advantages and disadvantages. And there's these discussions whether the world is continuous or discrete. And again, it's a question more philosophical than scientific, because uh, it's actually an ontological claim that we can address only with epistemology. So of course, our models are the ones that are continuous or discrete. Universe doesn't care whether how we describe it. Um, and I mean, uh, evidence is in favor of a discrete universe because of Planck's constant. Uh, in time and space, meaning that Planck's constant is like the minimum amount of energy, and let's say elementary particles seem to to be minimal units. We don't know whether they can be divided or not because we would need more energy than the one we can muster in order to collide, let's say, electrons or photons. From what I understand, also for time, there's like a minimum scale, like 10 to the minus 40 seconds. But in practice, I would say it doesn't matter, or I don't know what do you think? Because at the end we can approximate continuous equations or systems with discrete approaches like we do with computers. I mean, computers are discrete in time and space and values, but then we can approximate to any level of detail continuous systems. I mean, we say we do continuous systems with digital computers and they are discrete. So it's kind of a discrete modeling a continuous model. But we can do also the other way. We can have a analog computer with discrete numbers. Let's see. We, um, so, I mean, I would say it doesn't matter. Maybe in practical terms, it matters in some cases, but then if we're going to be pragmatic, then we can just say, well, sometimes it's better to have continuous models and sometimes discrete models, and then we should better just use both instead of trying to say which one is best. It's better to know their advantages and disadvantages. So, for example, continuous models usually are better for theoretical proofs and discrete for if we want like a exhaustive exploration of the state space, then we can do it with discrete models. If we have continuous models, we can't explore it exhaustively because it's infinite number of states. Sometimes discrete, they're so huge that they're infinite in practice as well, but in some cases we can explore exhaustively the state space. So yeah, I mean the state space, basically the variables of the model are different dimensions, and then all the possible values are the space. So we can explore it, and then attractors are those regions of the state space that capture the dynamics. They can be stable, like in pendulum. If it goes down, then this lower point is stable attractor. You perturb it, it goes back to it. If you balance it upwards, that would be an unstable attractor, meaning that if you adjust it precisely from initial conditions, it stays there, but a small perturbation kicks it out of the unstable attractor. You can have chaotic attractor like this. In the figure, it's Lorentz attractors. It turns out that all chaotic attractors are fractal, and there are many interesting properties. And then basins of attraction are all the states that lead to the attractors. And then we can divide the state space in terms of basins of attraction. If the dynamics are deterministic, then those divisions are sharp. If there's some randomness or indeterminacy, then you could be in some regions of the state space that, depending on chance, they could go one way or another, or let's say to one attractor to another attractor. And this figure is from Waddington about epigenetic landscapes. So imagine like a ball running down a ravine or a valley. Then depending on the crevices and initial conditions, it could go to one basin or to another basin. And Waddington used this idea to explain cell differentiation. So if we have stem cells or pluripotent, I mean, the ones that embryos have, and then they start differentiating into skin, muscle, bone, nerves, and so on, all the cell types that multicellular organisms have. And I mean, all the mechanisms of morphogenesis have been studied, and random Boolean networks also take inspiration from this idea of Waddington of attractors. And then the idea is that the different attractors in random Boolean networks represent different cell types. And I mean, I like this phrase from Mary Shelley's Frankenstein. Invention, it must be humbly admitted, does not consist in creating out of void, but out of chaos. So in a sense, chaos gives us information that can be useful. It's characterized by high entropy, which can be measured in different ways. Boltzmann-Gibbs entropy or Shannon entropy, which are equivalent. And they're characterized by constant change, they're fragile, limits our predictability, but it also gives us adaptability. And perhaps it was first described by Poincaré, Henri Poincaré, in the late 19th century. So the King of Norway launched a prize for physicists who could solve the three-body problem. The two-body problem was solved by Newton, law of universal gravitation, and that was mid-17th century. So it was end of 19th century, like, okay, more than 2 centuries. We're just adding one more variable to the equations. What could be so difficult? And Poincaré got the prize not because he solved it, but because he showed how difficult it was to solve. And this later became known as deterministic chaos. So in the 1950s, Lorentz, that, let's say, defined this attractor. It's a model of the atmosphere. And it's not that we don't know how the atmosphere works. It's just that it's chaotic. So for example, you cannot predict how many rounds a trajectory in this attractor. Let's say once you are in this attractor, so you know, okay, we will stay without any perturbation in that region of the state space, but you can't predict how many times it will stay in one of the wings or ears of the attractor before it goes to the other one, and then it can stay 1 or 10 rounds, and then it goes to the other one. So it's like the formal way of defining chaos is when you have positive Lyapunov exponents, and then it's like, okay, but what are Lyapunov exponents? Basically, it's a measure of how much a system changes. So you take similar initial states and you see whether their trajectories diverge or converge. If they diverge exponentially or greater, then Lyapunov exponent will be positive. If they converge, then Lyapunov exponents will be negative. Lyapunov exponents of 0 imply criticality. So that's more or less desirable for some systems. So basically, what positive Lyapunov exponents tells us is that small perturbations usually have drastic effects on the dynamics of the system. And in NetLogo, there are these examples of chaos. So for example, a billiard, if you just add a circle, since you cannot predict exactly where of course you can predict, but then at the end, it's an approximation. The exact angle at which the billiard balls, which in this case are turtles, but let's say will collide with a circle. Then here, let me see, where are the initial conditions? Well, they start like with very similar initial conditions. Yeah, so somewhere here they are overlapping, but then very minimal differences. They start diverging exponentially. So let's say when they bounce out of right angles or let's say straight lines, they don't diverge so much as when they collide with circles or curves or even more rough surfaces. So let's say this tells us that even if we have very precise measurements, small differences will diverge exponentially, so that limits our predictability. And then there are different flavors of chaos, deterministic, non-deterministic, quantum, and so on. rule 30 of elementary cellular automata. It's example of deterministic chaos we already mentioned. Quantum chaos was defined by Eugene Wigner, who was a teenage friend and high school classmate of John Neumann in Budapest. He won a Nobel Prize, and he's also well known for an essay on the unreasonable effectiveness of mathematics and many other things. Another interesting property of chaotic systems is their universality. So this so-called bifurcation diagram of the Poincaré section of the logistic map. So the Poincaré section, which of course refers to Henri Poincaré, is just basically showing which values on the y-axis belong to an attractor when you have an equation with this parameter, which is R. So the logistic map, it's equation y equals Rx times 1 minus x. So it's a parabola. And then the height of the parabola depends on this parameter R. When R equals 4, the height is 1. And then it's an iterative map, meaning that you iterate an initial condition, then you apply the equation, and then the value you get, you take it as your initial condition for the next step, and then you just iterate. So for values of R that are small, you have just one attractor. Let's say the dynamics converge to one point in this parabola. Then you have a bifurcation point, and then you have a cycle attractor of period 2. Then you have another bifurcation point. You have attractor of period 4, then 8, and so on. But then the bifurcations become smaller and smaller. So there's a limit in which you have orbits of period 2 to the, let's say, infinite, or it reaches infinite, and then you have chaos if you continue moving this parameter. But then you have windows of order. So for example, here you have a window of period 3, but then still you have a bifurcation point. So then you have period 6, then period 12, and so on. So actually you have all stable orbits of all natural numbers inside this diagram. And not only that, it's fractal. So if you zoom here, you will see again the same bifurcation diagram and periods of all natural numbers. So the natural numbers contain themselves an infinite number of times. And you have the same in all maps that have a single maximum. So if it's not a parabola, but just like a triangle like this, you will have a similar bifurcation diagram, and it's universal because the ratio of the bifurcation points. So if you measure like, okay, this distance over this distance, and then this distance of the next bifurcation to the next bifurcation, when that tends to infinity, it leads to a constant called Feigemann's constant, 4.66, something like that. And that applies to all logistic maps. It also applies to the Mandelbrot set. If you look at the diameters in the main axis of the circles, they also follow this ratio of the Feigemann constant. Why? It's a bit of numerology. But yeah, it's extremely interesting. Deterministic chaos, maybe a bit too mathematical, but it's good to know about it. And we already discussed a bit what's the difference between chaos and complexity. It says that chaos is characterized by sensitivity to initial conditions. Complexity, it's basically when you have relevant interactions. So the more interactions you have, the higher probability that you will have chaotic dynamics, but not necessarily depends on the effective interactions or how much change those interactions bring. I mean, if you have a model where interactions actually stabilize dynamics, then it's actually the opposite. No? Imagine a system where individuals are almost chaotic, and then you start adding interactions, but those interactions actually kind of stabilize. So then the more interactions you have, the less dynamics you will have. But of course, it depends on how you model things. But anyway, you can have chaos and complexity at the same time, or just one of them, like the logistic map, it's not complex because you just have one variable iterating among itself. With cellular automata, we saw that rule 30 is chaotic, but other rules are not chaotic. They're either complex or critical or ordered. Same with random Boolean networks, and they all have interactions. So we could say that they're all complex systems. And we can also have systems that are neither chaotic nor complex. And I mean, in a very general way, we can say that there's too few or too much change for any system, and then we want a balance between those two. So change is not bad. Too much change is bad. But also if we have no change at all, that's also not desirable. Then this precise balance is also changing. So that, of course, makes it challenging to study, because it's like, okay, if we find a optimum rate of change for a system, but then the system changes, then probably the optimum rate of change will also change. So we need constantly to adjust. So it's like the Red Queen in Lewis Carroll's was it in Alice in Wonderland or Through the Looking Glass? I forget. Red Queen. No? So there's this idea of the Red Queen that has to run just to stay in the same place because the world is moving. So yeah, it's a concept used or borrowed in evolution, because many species need to evolve just to stay on the same place, meaning to maintain their fitness. They need to adapt at the same rate at which the environment changes. So it's called as the Red Queen effect. So I mean, we can see that in the world there's impermanence, there's variation, there's transformation, and all of those lead to change. Interactions in most cases also lead to change. And if we have interactions going beyond a certain point, usually stability will never be reached in practice, especially for open systems. And then it's an open question how to achieve balance when change is constant. So yeah, it's useful to have neither complete stability nor complete chaos. And then we can say that if we can accept change, then we'll be better than trying to fight against it. And then just to conclude, we can say that change is prevalent. There are different flavors of it, different methods for studying it. But yeah, I mean, it's a huge area to study dynamics. This is just a brief overview, and there's much still going on. Okay, so for next week, you should upload your final project proposals, and there will be presentations on Thursday, so in 1 week, 5 minutes, and it's better if you have the presentation so that you can get real-time feedback. But even if you give a presentation, please record 5-minute video, share it on Brightspace so that everybody can comment on your presentations or your projects, and also please comment on the projects of your classmates. Slides are not compulsory. You can use them if you want, but they're not necessary. And the idea is to get better feedback. And then for the week after that, we will read papers about information. Actually, those two guys were linked to the other Epstein, but anyway. So yeah, one out of those 4 papers. Okay. Questions about this?
Yes.
No. Ah.
So, one presentation, if we were to prepare slides, what kind of aspects should we explain? Like, should we talk about the paper or how are we going about? Like, is there an outline you could help us with? One output person.
Yeah, so it would be useful if you start with your motivation rather than, we are just going to do this, but I mean, there's this book from Simon Sinek, Start with a Why. So it's like, okay, even if you didn't come up with idea in this way, it's useful to present it in this way, like, okay, why are we interested in this problem? And then to say, okay, what are we going to do? And then how are we going to do it? Or was it first how and then what? Yeah, I think it's first how,
Yeah.
and then
Or
what?
how far.
Yes. And let's say if you structure it that way, it will also become clearer because it might be that, I don't know, you find a data set or you want to do a model about some topic. But then when you start thinking, okay, why would we study this? Then it might be not so interesting. And then it's like, okay, either you find something interesting to do, or then you find some other thing that might be interesting, some other data set or model or things like that. Yeah.
I guess just a quick note, talk about that change thing. Remind me of the anti-fragile versus robust.
Yep.
Thing, right? Because we don't want change, but at the same time, we don't want too much change.
Mhm.
That's why we need both fragility and robustness. That's a clear idea?
Yes. So actually, I just put a comment in your comment on Brightspace, no, just before the class. Yes. So you were saying that you were saying about robustness, which will be somewhere here. But then anti-fragility, actually, it's not here, but anti-fragility, it's way here. So this balance between robustness, so few change, and too much change, which would be chaos or adaptability. It's too much adaptability, it's also not appropriate because then you lose the things that you already had working. Because anti-fragility, it's the property of systems that benefit from change, but you can say that they are very static by themselves, and then they benefit from perturbations, and together with perturbations, then they reach balance. But then if they are already here and you add more change, more perturbations, then they will become even more chaotic. So what we have observed in many natural systems measuring their anti-fragility is that they are actually ordered, and then they are more ordered depending on how dynamic is the environment. And then they are anti-fragile because with those perturbations, they become balanced.
But chaotic will give you more information. Sometimes that might also be beneficial.
Yes. So also, I mean, you will see that encryption and compression, they're usually on the chaotic side or high entropy, because you want to get rid of all the redundancy for compression so that you don't have, say, extra space, and for encryption, so that it's difficult to decode. If you start having regularities, then it's easier to decode from those regularities. Like a very basic encoding is if you just shuffle the letters in the alphabet. So you have a code that, let's say, every A will be a C. Well, no, even easier. You just shift the alphabets. So A, B, C, and then A will be M, B will be N, C will be O, and then you just shuffle. And of course, it could be not just shifting, but randomly assigning one symbol to a letter. But then since letters have different frequencies, like E is the most common letter in English, you have long text, then you just calculate the frequencies of your symbols and then say, okay, this one is most frequent, that's E.
We did this last semester.
Yes. So when you encrypt or compress, you lose those, those regularities of those patterns are harder to observe. And then there are also other ways of encrypting that it's actually adding redundancy or adding noise. And then you don't know which one is the noise and which one is the real information. But those are not used because then you need more space. But if quantum computers make other approaches complicated, then it might be useful to add information for encryption. And yeah.
Just that those two words are kind of similar, so I got confused.
Yes, this is that the more anti-fragility means that the environment is more chaotic, or there is more change in the environment, or the system can benefit from more change, but not that the system itself is highly chaotic or that there is lots of change in the system. But again, it depends on where to draw the boundaries, because if you would include environment in your description of the system, then it's already, you could say, okay, there's already change inside. Yeah.
Thanks. We can use any of that way for the project, and they're not necessary.
Yep. Joel, you had asked by email about last class whether it was deterministic or.
No, I forgot to send.
No, the cube.
I was telling us if we email me the extra grades or something like that, I just sent. But he was asking us to comment on, do we think if logging is deterministic or not deterministic? I felt it's the latter.
Yes. So, I mean, just like I briefly mentioned that there's this debate whether the universe is continuous or discrete, there's also the debate whether the universe is deterministic or random. And there are implications for, let's say, free will and so on. And I would say that in this case, it also doesn't matter, because you can have, in a similar way, a system that's non-deterministic, but then you can get predictability out of it, like with thermodynamics, or a model that is non-deterministic, and then you can get predictability out of it, and vice versa with deterministic chaos. The system is deterministic, but then you have so much information in there that prediction is limited. So at the end, it doesn't matter, let's say, to speak whether the universe is ontologically deterministic or not. There are some patterns that we cannot predict, and some aspects that we cannot predict in practice, and some aspects that we can predict in practice. So it doesn't matter. But then about voids, it depends. Because basically, if the model doesn't have any randomness, nor indeterminacy, which are different things, then it's deterministic. Even if it might be chaotic, like the billiard balls, you could say that, the voids are kind of clashing each other, and then if you change slightly their positions, then they will react in different ways. and then those differences will propagate in state space. So then it's difficult to predict, but still it's deterministic. Then, Zainab, you also commented about this, and it depends on the precise implementation. So, for example, it depends on how NetLogo evaluates the positions, because actually even when you have multiple voids, they evaluate the change one by one. So in cellular automata and random Boolean networks, usually we say they're deterministic because you update all the states of the nodes at the same time. So you have basically two arrays, one at time t and one at t+1. And then you update at t+1 with all the values of t. And once you update all the values, you copy t+1 into t, and then you start again. If you want to do it asynchronously, meaning that you update one node, and then let's say with that change, you update other nodes, then the order matters, because it might be that you first update one node, and then that gives you one value on the same node, and then you update its neighbors, and then that will give you a different value. So but let's say, then the question is whether that asynchronicity is deterministic or not. And in NetLogo, it's not deterministic because, let's say, to have statistical, to avoid biases, every time step, they shuffle the order in which they will update the turtles, the agents, because they update them sequentially. They don't do like, okay, we look at their state at the previous time and then we update all of them. They don't do that. They update one by one, but every time step they shuffle the order in which they get updated. So then if you start with the same initial conditions, then they start updating maybe first the voids on the left, and then they will adjust somehow, and then the voids of the right will be adjust differently. And then if you start again, maybe the voids on the right will be updated first, and then that will give you a different effect. So in that sense, the NetLogo implementation of voids is non-deterministic, but because of that, not because of the updating, not because of the model. The model itself, you could implement it in a deterministic way, but then you would need to do this updating of all the variables at the same time. Yeah.
Would you say difference between deterministic and non-deterministic is the amount of the level of the difference between the two systems is about the amount of clarity we have in it, as in the more variables you control, the more deterministic it becomes.
No, deterministic is basically when the change is defined properly. And non-deterministic is usually when you toss a coin somewhere and then that defines a transition. So then sometimes it will go in one direction and sometimes in another direction. So if you remember these state spaces of random Boolean networks, in the classical version where you have deterministic transitions, every state has only one successor. So if you are in one state, you are sure what will be the next state, which will be the next state. If you have, for example, non-deterministic asynchronous updating, then you are kind of throwing coins to see which nodes you will update. So it doesn't mean that, okay, now we can go into any state, but you can go into, in some cases, into more than one. And then that changes the state space because, as I mentioned, the basins of attraction start overlapping, but then you can also have loose attractors, meaning that you are in a subset of the state space, but sometimes you go into one state and sometimes into another state. And And you have that whether you have fewer or more interactions, fewer many variables. So that's more an inherent property of the model. And then non-determinism is different but related, and sometimes is confused. And it's simply when you don't know where the system will go. But that doesn't mean that the system is random. But then the representation on state space is also that you have one state, and from there you can go to many different states. So, yeah. The difference between non-deterministic and let's say undefined would be that non-deterministic, you are basically playing dice, or so there's some mechanism that will define this state transition. And in the other case, it's simply not defined, or you don't have enough information to know where the system will go. But it might be that it's deterministic or not. You just don't know. I mean, in computer science, it's defined like that. And then you can make some analysis if you have a state space like that, it's not defined whether it will go one way or the other. You still can do some operations without having that definition, that transition well defined. Yeah. Okay, so we have some time to comment on the readings. Who would like to start?